Hello and welcome to the video lecture series brought to you by St. Andrews Institute of Technology and Management. We are discussing the subject called Data Structures 2, and today we are going to start a new type of advanced data structures called M-way trees. Now, M-way means multiple way trees. I think from the name you can understand itself that what we are trying to do here. So this is what the definition of an M-way tree looks like. Let me read out for you. Now, for some integer m, known as order of the tree, each node is a degree which can reach a maximum of m, or other words, each node has at most m children at a particular node. So apart from this particular lecture, so every other kind of tree that we have studied until now, it's a binary search tree. Now, the binary word actually restricts the number of child a particular node has. Until now, the trees that we have studied in this particular course, the number of childs are actually limited to two. Now, why they are limited to two only? Because the name suggests that it is a binary search tree. So you have only two ways to go, either to the left or to the right subtree. But that restriction we have removed now. So our tree could have more than one children. But again, because we have not removed any other constraint or any other rules that we have followed in the binary search tree, that is, the value smaller than a particular node value should uh, descend down towards the left hand side of the subtree, and any value which is greater than the node value should descend down towards the right side of the subtree. So that particular let's say constraint we haven't removed yet. So how it is going to be possible that a particular node which can have multiple children at a particular time can have, let's say, uh, multiple ways to go down. So, especially at the time when, so I have to excuse me for a second. Okay, so let's get back to the definition. What we are trying to say here is that in this particular case, in multiple way trees, we can have more than one children uh, to be attached to a single node. But we haven't removed the rule that the smaller values will proceed to the left and the larger values in the node will proceed to the right. Okay, so that rule is still there. And then again, uh, in a M-way tree, a particular node actually can have more than one value. So a node in an M-way tree with a degree m can have maximum of m number of children, and then again the number of values in a particular node can be m minus 1 at most. So a node actually consists you can visualize a node as a key value pair. So your keys will be the values, or not a key value pairs, but let's say your key pointer pairs. So your keys will be the values that are situated in the node, and pointers as the name suggests, are the pointers looking for the childrens. So this is how it looks like actually. So this is an m-way tree where m has a value of 4. Sorry, m has a value of 5. Okay. Now, as you can see that the maximum number of children a particular node has is equal to 5. We have 5 blocks here, 5 pointers here. 3 of them are used, 2 of them are unused, but we can use them. And the maximum number of children, no, sorry, maximum number of values that are in a particular situated in a particular, let's say, node is actually 4. So we have total degree of this node is 5. So it reflects that the total number of children that it can have is actually 5. And total number of values that this node can have is actually m minus 1. That is 5 minus 1 is equal to 4. So that is why this particular node has 4 values, that is 18, 44, 76, and 198, and it has 3 active pointers and 2 null pointers. But in the nutshell, it has 5 pointers and 4 keys. So a particular node will have a let's say key pointer pair. So A are normally turned out as the let's say the pointers, and K are termed as, in this definition, as the key values. Okay. So how it goes, how what is let's say what are the rules in on what basis we are actually going to attach the children's like in the binary search tree we have only two options, whether if the value, let's say if this 44 76 190 is not there, in that case 18 is the only value in the node. In that case, anyone which is any value which is actually less than 18 will go towards the left hand subtree, and any value which is actually greater than 18 will proceed towards or descend towards the low the leaves towards the right hand direction. Okay, so this is how it goes. Now in this case, as you can see, we have placed each key with around two pointers, and that key actually divides you, or it appears to be dividing these two. It appears to be dividing these two pointers. So how it goes is that any value which you want to add to the tree has a value less than 18 will proceed towards the pointer which is actually to the left hand side of the 18, or immediate left hand side of the 18, not exactly left hand side but immediate left hand side of the 18. And the value which is actually greater than 18 and less than 44 will proceed towards the immediate right hand side pointer of 18 or immediate left hand side pointer of 44. Okay, so this particular pointer, which is actually null in this case, so any value which came let's say 19 in this case, so any value 19, if you want to add 19 to this particular tree, MWay tree, uh, so in that case the 19 you have, if you want to look if 19 is there in this particular tree or not, first thing first, in that case you have to look for this particular pointer here. Why? Because the value 19 is greater than 18, which is the first key in the node. Now we know that that this particular key is actually greater than uh, the first the value that we want to add is actually greater than the first key, that is 18. Now we'll look for the value in the second key. Now second key has a value that is 44, and 44 is actually greater than 19, so we cannot move to away move forward. So we know that our value is situated between the key first and key second. So we have two options: either we can go towards the immediate left hand side pointer of the first key, or we can go towards the immediate right hand side pointer of the second key. So immediate left hand side pointer is actually this pointer. Please follow the cursor, and the immediate left right hand immediate right hand side is this particular, and immediate left hand side is this particular pointer here. Okay. So I think you have got the point. So let's have some more examples how this complete tree has been created. So let us suppose we want to add this 186. This 186. So how we have described this particular tree in the first place is, first we have to search if this 186 is inside this tree or not. So how it goes is, first we'll start with the root node, and the root node has, as you know, has four key values. It as this is a five-way tree, that is the value or the order of this MWay tree is actually 5, so it can have maximum number of keys equal to 4 and maximum number of pointers equal to 5. So first we'll look for the first most key of the first root node, that is 18. Uh, it came out that 18 is actually less than the value that we want to search for. Then we move to the next key, then search again, or compare again. Then we move to the next key and compare again. Then we move to the next key and compare again. And as it has came out that the value that we want to search for is actually less than the last key and greater than the second last key in the root node. So in that case, we have option to came down either to the immediate right hand side of the second last key, that is 76, or either to the left hand side of the last key, that is 198, or the immediate left of the last key, that is 190. So this is that pointer. Now it points towards this particular node. Now this particular node, again we have to search if the value that we want to find is in this particular node or not. So in that case, what we will do is we'll again start comparing the value to be searched for with the first key in this particular node. The first key in this particular node is 80. So it came out that our value is actually greater than 80. Then we'll proceed to the next key and then proceed to the next key. And it came out that our value is actually greater than all of these keys, and will fall of the node. And in that case, how the route will be proceeded is, as the value that we want to find out is actually greater than the last key of the node, in that case, the immediate right hand side or the last right hand side pointer will actually point the route towards which we can hopefully find the value that we are looking for. And I am saying that hopefully, it is not that it is going to be there or not. We are just hopefully we are going to find that value or not. Now we came down to this leaf node. Now leaf node, as you can see, that all of the pointers are actually null. It means they are not pointing to anybody. As in the case of binary search tree, all the leaf nodes do not possess a children. That's why they are called leaf in the first place. Okay. So next is, we'll again start searching from the first key. We'll start looking, comparing our value to be searched with the first key, that is 148. As we know that we are actually looking for 186. Okay, so we know that the value 186 is greater than 148, so we'll move forward, compare it with the next value or the next key, that is 151. We'll again find that it is greater than 186. We'll again move forward, and in the last place, the value exactly matches with the value that we want to find, or the key exactly matches with the value that we actually want to find out. So it is 186 actually. Okay, so this is how the addition, or not addition, but this is how a structure of your MV tree is organized. So, or you can say this is how you can traverse from inside an MV tree. We are going to see the addition of a particular key pointer pair in a particular MV tree in the next lecture. But this is how you can search a particular value in the MV tree. Now, if suppose we want to find out if 198, or not 198 but 199, if 199 is there in this particular example, in that case, how we have to follow? We'll start comparing the value from the root node itself, that is with the 18, with the 44, 76, 199. Okay. Now, since the value 199 that we want to search is greater than 198, we'll follow the right hand side pointer of 198, or the rightmost pointer of the root node. We'll proceed to this particular node. Now, in this particular node, we have only one value, that is 262. Let me remind you that this is a 5-way tree. The maximum number of children at a particular node can possess is capped at 5. That is, it can have maximum number of children equal to 5. But minimum number of children, will have no capping. There is no capping on that. So that is why this particular node here has only one key and 2 pointers. But that is actually in the permissible limits. That is from 0 to 5. 0 to 4 for the keys and 0 to 5 for the pointers. Okay. Now T62, we want to find out the value 199, and we know that 262 is actually greater than 199. So obviously, we'll proceed to the immediate left hand side pointer of the 262, which is actually null, and it indicates that we have actually, there's a term for this, we have actually fallen off the tree. We have actually fallen off the tree. It means that there is no value that we are looking for. And if there is no value that we are looking for, then your search algorithm is actually going to return to you null. That means the value that you are actually searching for is not in there inside the tree. So this is how you can, I think you have got the idea what an M-way search tree is. It's just an advanced version of your binary search tree, in which we have more freedom regarding the number of children and orders and all that. It does actually follow some of the rules to some extent of a binary search tree. It is, let's say, it's an extension of your binary search tree. Okay. Now this tree is not a balanced tree. We'll have a balanced M-way search tree called B trees further in the course, but I think you have got the idea how we can search a particular value in your binary search tree. sorry, in your MV search tree. So in the next lecture, we're going to see how to add a particular node in your MV search tree. Okay. So thank you.